Hello Internet, welcome back to our 2D voxel terrain video series. So last video we got started and we started building a quad tree which is actually going to house our voxels. In this video what we're going to do is we're actually going to make it useful. So you can see we have a quad tree. It just looks like a grid, but it's actually a bunch of subdivided squares, not rectangles. Squares are rectangles. They're still rectangles. Good to know. So anyway, what we have is we have a bunch of subdivided rectangles. It's a quad tree. Problem is, there's no way to insert things, there's no way to look them up, and there's no way to do anything else with it. So this is useless. But we're going to fix that. So what we're going to do is we are going to be focusing on making this into a sparse quad tree, which means only data that exists is going to be in here. So pretty much, since there's no actual data in this tree at all, we don't want any of this to actually exist. And so we should be able to do that really easily. That's all we need to do. We need to just not subdivide the nodes. And so theoretically, if we do that, we just get our outline, so this is sort of the starting place we want to start with. And so what we can do after this is, as we put things into this tree, as things fall within it, we're going to subdivide, but we're only going to subdivide those specific rectangles that are related, that the object is in. So when we place something, we'll subdivide this one and create 4 more regions. And then whichever one it falls in, we're going to subdivide until we get to the minimum amount. And we're going to do that so long as we're not at the minimum or the maximum depth. So that kind of increases the difficulty of our subdivision, but it means we don't have to regenerate the entire graph every time. And that's pretty powerful. So we've got a position, a size, and a depth. We don't need any of that. What we do need, we've got types here, and our quad tree node is storing a type. How do we want to do this? So there's really 2 ways we can do this. Since we're making a voxel terrain based around this data structure, it actually makes sense for the data type, our generic T type here, to actually be associated with the node. If we were doing this for like tracking something else, you may want a collection of things inside of that. So we are not so much well, actually, I think we can make this work. I think we can support that. So we need to add support for a few things here. Get index of position, don't need that. What we do need are some basic functions. I'm just going to actually start with one. We're going to do a void, and we're going to do an insert. And we're going to insert a type, whatever the type our tree is, we're going to put that into our tree, and we're going to give it a position. We need to give it a position so it knows where it actually is within the tree. Otherwise, this data structure is not really the right tool. So once we have that, we want to drill all the way down to the maximum depth and then actually assign the value of that node equal to this T type. And I'm not sure if we want it to stay a list or if we want it to just represent the T type. I think it might make more sense if the value could only be of the type of our node. And the reason I'm saying that is because if it's only able to be that value, that'll work better for our terrain, because that will just be our voxel. Then that'll be our voxel type, whatever that ends up being. Probably end up being like an enum value or something like that. So there's nothing else going on here. So we want to subdivide, and that means we're going to have to do a depth of our subdivision, and we're also going to have to pass in a target position and a type. So we should probably make these align, otherwise our functions aren't going to be very nice. And it's not going to like this either, because we have a default depth here. So if you provide a default value, those have to be at the end of your function, otherwise it doesn't work. And that's just because if I leave this off now, if I leave the depth off, it just assumes we're at 0 depth. So that's what that is for. So now that we have this, we'll get to that in a second. We need to actually call it with our insertion, which is going to take the root node, and we're going to subdivide with our position, our type, actually our value rather, that's what it is, our value, and then we don't need to provide a depth, do we? Oh, it runs towards 0. I get it. So a depth of 0 for a subdivision would mean it would only do one subdivision and then stop. So we want to do that and actually provide a depth as well. Then we need to change our t-type into our value so the names match. And then I'm just going to align this so that the arguments are in the same order, just so there's consistency in the APIs we're using. There's no real other reason to do it, but we're going to do this. What else do we need? We want to subdivide. And then this is a recursive subdivision, so it's going to keep subdividing down. What we want to do is we only want to attempt to insert it, or we only want to subdivide the node that we're inside of. Which means we are going to want to get the index of the position, which is going to be our, let's see. So we've already subdivided everything. This is a for loop. So we can actually get the index of the position first, and then if our index aligns with the index here, then we know we need to subdivide that node. All the other ones we can just ignore. So they won't have the data in it. So we're going to get the position. Our lookup position is going to be the target, and the node position is going to be our current position, I believe. Cannot access in static context. Got it. Private. What is this? Yeah, this can be static. That's fine. So all this is doing is this is actually from our octree. This code was not really changed. And all it's doing is deriving the index from our current position and our lookup position. And to do that, it's going to actually grab, where is it? It's going to grab, sorry, I'm missing something. From the index, I didn't scroll high enough. The Quadtree index, that's what we're looking at. We're trying to derive this from these values down here. And we might be able to do a cast to that, but I don't think that matters, so we're not going to. So now we have our subdivide, or our subdiv index. If the depth is greater than 0, which means we're not all the way at the bottom, and our subdivision index is equal to I, so if this is the node we want to subdivide, then that's what we're going to do. We're going to subdivide it, and we can recursively just pass down, our target position and our type. This should be called value, sorry. There we go. And we can move that. And so this should only recursively do that here. So then the only other thing we need to do is actually connect to it, I think. And so we can do that with a public transform array. And these are going to be our points. And so what we do is when we draw our gizmos, we actually regenerate our quad tree. And so what we're going to do is for each point in our points, we're actually going to insert each of those points into our quad tree. And so that way we can test that this is actually working correctly, because we can just configure as many points as we want to test and then plug them in, and it should work. So we've got our for each for our point in points. We just want to do a quad tree, and we want to insert our point with a value of anything. So right now we're not really using this, so doesn't really matter, honestly. But I'm going to actually change this to a Boolean. So the point is not going to work because it's a transform, so we need the position. So we'll get the world position, and then we'll use that to actually calculate this. One of the interesting things is that because of the way we're actually indexing into things and just checking greater than or less than, even if you're out of bounds of our quad tree, you'll end up actually inside of it, just right on the edge. So if you go way outside of it, you will end up on whatever node is closest to it, which isn't necessarily correct, but it will prevent us from getting any weird errors. What is this doing now? It's expecting an integer tree. We're not going to give it that. So if node is not leaf, and then we want to skip all of the subnodes that aren't null. And so we're just adding these checks in just to make sure that nothing crazy goes on, because since we aren't filling out our tree, it's very possible that things may not necessarily be at the end. So I think that's it. I think we can play with this and actually see what happens. No, we can't. Line 27. We didn't initialize our array. That's my bad. 0 element array, that should work. And now we can start this. And it should be less angry at me. It is awesome. We're getting our quad tree again. That's also good. So I'm going to create a point, access our quad tree. Doesn't like that because we have a null point, which we aren't handling right now. But now we have that. And so I should be able to move this around. And what we would expect, obviously this isn't working, but what we would expect is we would expect it to subdivide down to this point and nowhere else. So these would still be empty, but then this one would still work. So what we need to do is we need to actually figure out what's broken. I believe our subdivision is broken, but I don't know why. We insert our point, and it should be inserted and should bubble down. assuming this happens. So I'm going to actually stick some log statements in here just to kind of figure this out. We could use Visual Studio's debugger, and we may try that. But I'm going to stick with logs for now, just because I'm interested. Subdivide the element. I want to see if this is ever called, because I'm suspecting it never is. So it looks like I was right. So we're never subdividing here. But that doesn't make sense. We have to. No, we aren't. Because, so the first subdivision happens automatically. Oops. So we automatically will subdivide, do this one, and then we'll check to see if we should recursively go any deeper. And so what seems to be happening is this is always false. Which means, I imagine this is wrong. Let's log our division index. So how does this work? We create new nodes, set those up and assign the node, and then see if we should subdivide that node. I'm intrigued. So our subdivision index is 3, 2, 0, and 1. All of those seem valid. So I'm wondering why this is never happening. I'm gonna have to jump into our debugger. This may not run entirely there. Well, that was quick. I was gonna say this may not run entirely like how we would expect, simply because it's actually debugging the gizmos, which are always running. So I don't think we'll be able to get out of this now. If we continue, we'll just hit it back again. But that's fine for our purposes. So we want our subdivision index. Oh, our depth is 0. Why is our depth 0? I get it. We're causing this. So our insert is using the depth. We're not saving the depth of our quad tree ever. And because we're not doing that, this depth was 0, so we weren't ever, this initial condition was false. This depth greater than 0, depth was equal to 0, so that was obviously false, which was causing the entire thing to fail. So now, after this, it's backwards, but it's kind of working. And you can kind of see what we're going for, ish. It seems the vertical seems broken, but horizontally it seems correct. So all we need to do is fix our vertical. It seems to be either doing the opposite and doing the max of whatever it is, which isn't correct. But what you're seeing here is we're only subdividing the ones that we need to. So we only have detail where we need detail. So if we're rendering terrain, for example, and there is like a giant ocean, you don't need all of that information to render the ocean. It's just a plane or whatever. So what this gives you the ability to do is to get really specific detail at certain parts, and then the parts where you have no information, the parts that you don't care about, it allows you to discard those and not really care. So in this case, since we're building a terrain system, a 2D terrain system for platformers, this is going to be all of that sky components. So you could have really tall cliffs or something, but if you have everything else just sky by it, then you can just kind of leave that empty and not have to waste all the time and space rendering it. So I think this is good. We just need to figure out why our y is broken. It seems to be maximizing both of them, but our x seems to be working correctly. So what did we do differently for the two? I imagine this is the issue. Let's see. I remember with our octree, I really struggled with this logic. Like I struggled with this first video, but anyway. So if our lookup position.y is greater than our node position, so if we're looking for something greater than our node's center, then we want to look to, which is going to be the bottom, which is going to be wrong, right? Because we're looking above it. So this actually needs to be a less than. So the reason this is happening is because our lookup position is where we're trying to find, and our node position is going to be the current node. And so how we use this function is we take a current node, and then based on that and the position we plug in, we try to find which of the subnodes inside of it is the one we need. And so this was flipped, which was causing it to either maximize or minimize. So theoretically, now it should work, and it does. So now we have a sparse octree, which means we can insert things. I should be able to copy this point and stick another one on. And then we can, maybe not. We need to be able to support at least multiple points. We're not going to be doing this kind of thing. We're actually going to be setting it once and not keeping references to this. We'll probably write maybe a Perlin noise function or something to actually generate the terrain. But what this is doing is it's only drawing the second point, which is wrong. And why is it doing that? Oh, I get it. So we keep subdividing here, but our subdivide is actually a destructive operation, which means whatever was there before is now gone, and we're replacing it with this new version. So we need to fix that because we don't support multiple inserts, which is kind of the entire point. So how do we do this? Good question. So we obviously we can't subdivide there. That's not going to work. So we need a function if so if our subnodes is not or is equal to null, so if they don't exist yet, then we are going to create them. Otherwise, so the create is going to be all of this. So that entire function is sort of our generation. If it already exists though, we still want our subdivision index. That's something we still are going to need. And so what we're going to do is, if it already exists, and then if it already exists, do this. So if our depth is greater than 0, And then we don't need to do the subdivision index because we can actually just force the subdivision on that index. So we can subdivide our subdivision index like so, which makes me think that I can take all of that away. So we don't need any of that. So what this will do is if our nodes don't exist, this code right here is going to generate the new nodes. It's going to subdivide our quad tree into 4 separate squares or rectangles or nodes, whatever, and then it's going to assign them to the new array. If that already exists, we don't care, and all we want to do is just do our depth greater than 0. So if we should subdivide, then we subdivide on the subdivision index, which is going to be the index we want to subdivide on, and we calculate that up there. It's the same thing we were doing. We just removed that condition and just explicitly said there shouldn't be any changes here. The only advantage to this is now we're not overriding the quad tree array we were making, because previously every time we called subdivide, it was going through and it was actually resetting the subnodes, which if we had already set it would override it. So now that's gone and this should work. So I'm expecting 2 of them. And so that works. It's a little bit laggy, but that's because we're regenerating this a lot. And so hopefully that will go down as we stop needing to regenerate this entire graph over and over and over again. But the cool thing is that it works. Yeah, that's really laggy. My bad. So we'll have to play with that to see if that's actually lagging because our data structure is slow, or if it's lagging just because we're re-rendering it constantly. But I don't really know which is which. But for now, I think this is a good place to leave it, because we have it demonstrating that we can actually insert data, and we can also not render data. So we have a sparse quad tree now instead of just our normal quad tree that was constantly full of data, and we can actually do inserts. We don't have deletes, but we don't need deletes for what we're doing. Well, do we need deletes? Yeah, I think we'll probably want deletes. Those may be more difficult, but we'll have to play with that and see what happens. But for now, I think this is a good place to leave it, and then we can work on actually generating things in the next video. So we may have to. I've been thinking it might be interesting to do some noise calculations to actually randomly generate our terrain. I was just going to use a image map to kind of build it, but it'd be pretty cool if we could just give it a function and just say make me something. And I think we can do that. So that may be a tangent we end up going on, because I think that'll be fun. So if there's something you guys want to see, let me know in the comments. I'm kind of building this based off of what you guys are saying about it. So if there's something you guys would like me to do, or something you think I should change, let me know, and I'll see what I can do. But I think that's it for this. So until next time, see you, Internet.